All right, good morning. Last time we were looking at perceptrons. And so we had our inputs, we had our function and the calculations that we were going to do to decide about classification, and then we had our output. So we would have something like our inputs were X, Y, and 1 as that default for bias. And all of that feeds into our hidden layer where the calculations take place, and then that leads to the output. There were weights on each of the input layer, on each of the inputs. Excuse me. And so what happened in the hidden layer is we would do the dot product of those weights with the input vector x. Let's call it vector like that. And so you would have the input, and in this case we would consider all three inputs, the x, the y, and the dummy variable or the bias variable with input of 1. And then we would check to see what happened with that. If this was positive, then we would output a 1. If this is negative, then we would output 0. And that would determine what happens over here on the right-hand side as the final output. Okay, so we were looking at the basic logic functions, excuse me, and, or, not. And so, for instance, we looked at or, and in the case of or, we found a couple of ways to do this. And one way that we saw you could do this with or was if we made these weights 1 and this weight -1/2. Put in whatever the x and the y values are. These are Boolean variables, Boolean values, 0 or 1. Put in the appropriate x, y values, the bias input of 1, but the actual bias weight of -1/2. And we saw this gives the right answer. And what I asked you to do was to do the same thing. We did and as well. With and, we could make this work by making the bias weight -1.5. Again, other ways to do that. So for and, it would be exactly the same, except the the dummy weight could be -3/2 to make everything work out. So what I asked you to do was to look at XOR. So what happened with XOR? So Joe says you can't do it. And of course, you know what I have to say. And of course, I guess I hit caps lock at some point there. So what do you think, Joe? Okay, so let's take a look at XOR. What does XOR mean? Okay, so XOR means one or the other, but not both. And so if we had some situation of A XOR B, then that would mean, so one or the other, what is that? That is A or B, but not both, so that's and, not A and B. So one or the other, but not both, looks like this. All right, so one or the other, not both. Oh, okay, great. I erased everything. Well, okay. So let's do this in the let's just rewrite this in a slightly different order to make some things a little bit easier to work with. We could have said that in the other way around. Not both and one or the other. That doesn't change anything. But since we're thinking of these perceptrons really as a function where you're inputting things, we could do this. What are we doing? We are ANDing together these two things. So these are the inputs to an AND function. And inside that function, we have, well, so we're just trying to see what's happening, right? So this is the meaning of this A XOR B. And so we'll see in a minute that actually with the single perceptron, Joe, that you're right. You cannot do it with one piece, but so we're going to string it together instead, and then we're going to back up and see why we can't do it with one. Okay, so do you see I've rewritten XOR in terms of like a function idea. So what do we have? We have in here, we're going to do an A or a B. We're going to do, well, first on the inside, I guess we'll do an A and B, then we'll negate that. And then we're going to put that together with an A or B. So what do we have? We'll have A, we'll have B, and for now, I'm going to leave out the bias variables because they're going to show up multiple times there's a different bias variable in as each piece as we're stringing it together. So we'll have A and B. Then what do we need to do? We have, at this level, there's an A and B, and at this level, there's an A or B. So those are both on the inside. Actually, here, let's put it there instead. So the A and B and A or B are both kind of interior functions. So let's take both of those to an and both of those to an or, and treat these as two separate, basically two separate perceptrons. What do we need to do with the output of the and? The output of the and where does it need to go? Yeah, it needs to go to a not. The output of the or, if we're keeping like levels the same, the output of the or could go to, yeah, a not, right? If we really wanted to do that, I'm going to just put a blank box here that doesn't change anything, because we want to really not have an effect on that output. What happens to both of those pieces? Both of those pieces go to an and then what happens? That goes to our output. And so what happened? It turns out that in this case, that we really can't, and we'll see in a minute why you can't actually do it with one perceptron. But we're going to take our true-false values, feed those in on the left. Then we have actually two hidden layers, but on part of one of those layers, nothing much happens. Then it goes to another hidden layer before the output. So by stringing these together, by stringing these perceptrons together, just building them out of the basic pieces, we can get XOR. Okay, so why can we not do that with a single perceptron? So this is the whole idea of a neural network then, basically. Stringing these pieces together so that we can get what we want to happen at the end. Now we can't, okay, so what we haven't done in this case is we haven't drawn in the biases. Each one of these really have an extra input at each place that could have different bias values. And we haven't talked at all about how to calculate those values other than what we already did by hand. By hand, we calculated some weights for the inputs and a bias weight, and so we would just use those same weights in this situation. But what if we wanted to build XOR without those weights? We'll put that off for a few minutes. Okay, let's take a look at OR, and let's look at the truth table kind of outputs of OR. I'm going to draw this out in kind of a grid so that we can see the the results of true and false values. With OR, if we put the true false on here like this, what do we get? This is a false value. True, true, and true. Is that okay? So you're thinking of this maybe as a 0 and 1, right? False is 0 and 1. So you're thinking of it maybe as just drawing things out on a in a plane. Now, if you notice, we can separate the true values from the false values. We can draw a line right here to separate the true from the false. Now remember that we said our weights in our perceptron could be 1, 1, and negative 1/2. That was a good example of weights, or an easy choice of weights for this. So let's look at this orange line. And if we're thinking of this as just zeros and ones on the interval 0 to 1, and looking at that line, see if we can find an equation for this line. This line has slope what? Yeah, it has slope negative 1. And what is its x-intercept? Yeah. What's the y-intercept? Right? In both cases. So I mean, we're just kind of guesstimating it, right? But so we have these intercepts. They're both 1/2, and the slope is negative 1. So if we write this in slope-intercept form, y equals mx plus b, what do we have? We can think of that as 1 times y, and m is what? Negative 1 times x, and then plus 1/2. What if we put all of this on the left-hand side? If we put all of this on the left-hand side and write the equation in standard form, where you get things equaling 0 on the right-hand side, we get 1 times x plus 1 times y minus 1/2 equals 0. And that is not an accident. Yes, I'm sorry, I did put an x instead of a y. Let me rewrite that. Thank you. There we go. Okay, so what that process of calculating the weights on a perceptron is really doing is recalculating an equation for a line that will separate one category from the other. If we did this with and, same situation. What do we have here? We end up with false on everything but up here. And what does our line look like? Our line needs to come up here to separate those pieces. And so if we write it in the same format that we just had, yes, so Alex wrote down an equation in slope-intercept form. So if we write it down in the other form, in standard form, looks like that. And again, we get the weights that we said work. Now there's other ways, so we can have other equations. There are other lines that do the same thing. It's not the only line, but it is a line that separates. And so what we have are these solutions or these class categories. True is separated from false by a line. Let's take a look at XOR. Now, you could change the order of trues and false, and it doesn't look like these are separable. So we need to make sure that if you say that you can't do something, you need to make sure that you actually can't do it no matter how you organize. But what do we have with XOR? I'm just going to write it in the same order here. What do we end up with? False here and here. True here and here. And what happens if you try to draw a line to separate these? If you try, how many ways could there be to reorder or organize the trues and falses in this case? How many ways are there to swap them around and get different pictures? If we, for instance, traded true and false here, right? If we traded those, that would be a new picture. Or if you traded them here, that would be a new picture. So how many versions of this drawing could we get in all? Yeah, 4 different things that we could, there's 3 more, right? So there are 4 in all. And what happens with every one of them? With every one of them, you get this idea of um, the diagonal thing, right? The trues are on a diagonal and the falses are on the opposite diagonal, no matter what you do. And so there's no line to be able to draw to separate these. So XOR is not what we call linearly separable. And it turns out that the only thing that that a perceptron can do is deal with linearly separable things. Okay, now linearly separable, we're looking at this in 2 dimensions, so we're actually drawing a line. What if we were looking at something in 3 dimensions? What would we be separating them by? Yeah, in 3 dimensions it's a plane. In 4 dimensions it's a hyperplane, right? It's a higher dimensional version of a plane. And so this orange line is called a decision boundary. And so our purpose then is to, with a perceptron, when we're calculating these weights, is we're actually calculating an equation of the decision boundary. And so that's why you get the greater than 0, less than 0 idea. You're saying you're above that line or you're below that line. And one question that comes up is what happens when you're right on the line? So if you have something that's right on the line, what do you really do? If you have something that's right on the line, um, find a better line. If you can't find a better line, then that sometimes leads to some issues. But so does this seem like anything else that you've ever done with drawing a line between things? So any other situation that you've seen um, in the past 4 years of drawing a line between things to does seem vectory. Have you ever used or seen or heard the terms the separating axis theorem? Okay, so maybe sounds familiar. What is its purpose? Its purpose is one way of dealing with uh, have two objects intersected. Drawing between them, but you know they haven't intersected. So there you go. And so it's all related, right? That I mean, that's something from graphics. It's a hit detection thing. Seeing if these two objects are overlapping. Now, not everything can be tested in that way, but some things can be. And that's the same situation that we have with perceptrons here and with this decision boundary. Not everything can be classified in this way, but some things can be. And the things that can be, we work with them. The things that can't be, we can do what we just did with XOR and glue a bunch of these smaller pieces together and still uh, make progress, right? Whether or not we can completely solve the problem. But what happens in the other situation? Where we're gluing these together, then the boundary between the things aren't straight lines. The boundary is who knows what the boundary might look like. It might be like we have down here in XOR, that there's more like a an ellipse you can put around one situation, but not in the other situation. Okay, so what's our goal? Our goal is to be able to figure out how to get these weights is how to figure out we need to figure out how to get these weights without actually doing what we did last time of calculating the weights. We also want to do it without necessarily looking at the math to try to calculate the weights from something from an algebra class or something. Um, and so we need a way to be able to update these weights, start with some random weights, and have a calculation that will do an update. Okay, so here's what we do. All right. Anyway, excuse me. All right. So here's what we need to do. We need a process to update the weight, and so there is a weight update rule for perceptrons. We're going to start with just maybe some random weights. And what we will do is we will decide an update rate. Call it alpha because it's always written in like math notation. So an update rate can be anywhere from 0% to 100%. But so it's anywhere from 0 to 1. But if you update with an update rate of 0, then you're never updating weight, so there's no point in doing it. If you update with a rate of 100%, or so, if you set alpha to be 1, you can run into some problems where you've updated too quickly and you converge to the wrong answer. It's like we saw with genetic algorithms when we got something that worked in a local situation, but we'd get stuck in a rut and we couldn't get out of that. And so usually we don't make alpha too big, but we have to decide how big to make alpha based on how much data we have for training and so on. So we'll deal with that in a little bit. So we're going to update weight I. Maybe we'll do it like that. So oh, you can't see that yet, can you? To update weight I, we're going to take the old weight I, and then we're going to modify it a little bit. We will add alpha. Okay, we'll define what these terms all mean in just a second. So what we're going to do is we're going to update a weight, we're going to take the original version of that weight, the last time through, and multiply by something. Okay, so the alpha is how much of the potential difference we're going to take into consideration. Y is the output that we actually wanted to get. And h of x is that dot product that we were talking about last time. So remember, not just the dot product, it's if the dot product is greater than 0, make it 1, otherwise make it, let's try that all again. So this function h is the Heaviside function, named after a guy named Oliver Heaviside, who did a whole bunch of work in physics and maths and electricity back in the 1800s. And interesting guy. So look at Oliver Heaviside. Look him up. And so, excuse me. So that's the thing that we had already done. So what happens here? We are going to look at the difference between the output and the the value given by the dot product. And then multiply that by the input value. Now, what are we talking about in this case? We're talking about the inputs are binary right now. So these inputs are just zeros or ones. And so this idea is how close are you to, if you were supposed to get a 0 and you got a 1 instead, or you got a 1 when you were supposed to get, whatever. You got the wrong thing. You got a 1 when you needed a 0. You got a 0 when you needed a 1. Then you would make a corresponding change. What if you had the right thing? If you had the right output, then this part is 0. And so if you have the right output, then all of that is 0. What happens to your weight? You don't change it. You only change your weight when there's a mistake. Now, the way this works is we have our perceptron set up, and we feed in a piece of training data. So we set up our perceptron and we put arbitrary weights on it. We put in a piece of training data, see if it gives the right answer. If it gives the wrong answer, we update the weights according to this formula. If it gives the right answer, we go to the next piece of training data and we see if it gave the right answer. And if it gives the right answer, then we keep it, and otherwise we update. And so our process is this kind of online training where you're working through the training data and updating the weights correspondingly. Now, alpha, in this case, the training rate or the update rate, alpha can be a constant. So you say, we're going to do 20% of the possible change each time. Or we're going to do 40%, or we're going to do 10%, or we're going to do 100%. So it can be a constant, or sometimes it's function-based so that it decays over time. What would it mean for alpha to decay over time? That means it's going to get smaller and smaller as time goes by. So what would that mean, do you think? Yeah, as it gets more data, as there's been more training, it learns a little bit less from new data than it did from the data that it already had. And so it's kind of like what happens when you are learning something new. What happens when you're learning something new? You learn a lot at the beginning really quick, maybe not quite that steep, but you learn a lot at the beginning really quickly. And then over time, you learn less. Maybe not quite so steep. That's a really steep learning curve in that situation. But what happens the more of that you know about something, then up here though, right, Walter? Well, not quite horizontal. Horizontal line up here where you already know all of it going in, so you don't have. So what happens if you have an alpha that decays over time? Then maybe maybe not this picture, but you would get something that is that the learning isn't as extreme the further on you go. You learn less from one new data point than you have from everything that you've seen before. Okay, so what's going to happen in our formula here, in our update formula? If the output is correct, then the weights remain unchanged. Okay, so that's what we just said. What if the output is supposed to be 1, but the h of x value is 0? What happens with this? What's going to happen? Well, y minus h is going to be a positive number. So what's going to happen to w? Okay, so what's going to happen? Y minus h back up here in our formula would be positive in this case. Alpha is a positive number. So the weight would be increased when the xi value is positive, and it would be decreased when the xi value is negative. And that makes sense since the goal is to make the dot product bigger so that the h becomes 1 instead of being 0. So what are we trying to do? We're trying to adjust the weights so that the dot product becomes the right answer. On the other hand, if y is 0, but the h value is 1, then what would happen? Just the opposite. So again, we're trying to adjust this so that the weights correspond to giving the right answer. Okay, so what could we do? We could build a generic perceptron if this is completely for binary input, instead of saying then the negative part doesn't come into play. So it would just be on the positive value, but it would still adjust the weights accordingly. So what do we have? We would have, maybe we wanted to create a perceptron for OR. And so we would have, this input down here is always a 1. We would have zeros or ones as the other two inputs. We would have weight 1, weight 2. And again, usually the idea when this is done is that the bias is the weight in the 0 position. And that's just so that, I mean, you can put it at the beginning or at the end, but often it's done in that way so that when you write down the equation in standard form, we would have written this equation earlier like that. And so it would just be reading those weights in that order. So it doesn't matter where you put the put that weight, just knowing which one is the bias and which ones correspond to the other input. So if we did this and starting with some random values as the weights, again, usually starting with binary values, or in other situations that aren't binary, we might start with just numbers between 0 and 1. The weights might end up getting bigger than that. And what would we do? The Y is the correct output, and so we're checking what should we have gotten for did we get, and that will work backward to update the corresponding weights. So when we have data that is linearly separable, process does what it's supposed to do. It converges to weights that correspond to the coefficients of a line that separates those points. Okay, and so what happens is this process works if the data is linearly separable, and if it's not linearly separable, then it doesn't work. It either goes on forever. Yes, that is the a result of this, that perceptrons can solve any problem where the data are linearly separable. So it corresponds to those other perceptrons, things that are not XOR, and there's other things that are not linearly separable. But of the basic ones that we talked about, this process will give you the right answer for and, it will give you the right answer for or. Excuse me, in terms of the correct weights. Now the question is, how long do you have to run? How much data do you need in order to get the weights to be updated correctly, and so on. So if you had a lot of data of different types, not talking about and or, but if you had a lot of data that was linearly separable, you might need to train your perceptron for a while. You might need a lot of input data in order to get those values to be just right. But again, we have the same kind of question of how much training do you do? Can you overtrain, and so on? And you can do that. You can overtrain. So what happened in this process? We have these linear classifiers, right? The end result, a perceptron is going to be able to classify things that are linearly separated. And so linear classifier, these are the examples that we've seen before in Lab 7, they give a completely confident prediction. Say 0 or 1. They say occupied or not occupied. They say true or false. They give this one answer, no question, here's the answer. And this is true even for data that are very close to the boundary. What happens if data, for data close to the boundary, that boundary might not be perfect. It might be a little shifted. And so it could be that if you shift it just a little bit, that a data point would jump from one side of that line to the other side of the line. I mean, the point's not moving, the line's moving, but it'd be on one side of the line or the other side of the line. And so if our line were a little bit wrong, it could be giving wrong answers for some of the data close to it. And so there's another approach. Instead of using the Heaviside function, another approach uses the logistic function. The logistic function I'll use, well, maybe just spell it out. Logistic function of some input is 1 over 1 plus e to the negative z power, whatever the input was. Okay, so 1 over looks like that. Have you seen that recently? Okay, so I just drew a picture of one of these a minute ago, and you've seen or heard this maybe if you've been paying any attention to news. This is the way the virus spreads quickly at first, and then slows down as we go further. And so this curve looks something like this. All right, and we're looking at just the part of it between 0 and 1. And so rather than the Heaviside function, which is a step function, the step function just jumps from 0 to 1. This function has an increasing, and again, it's a little steeper. The drawing is a little steeper than it should be, but it moves up and then levels out. And so, what do? We calculate our value. And instead of once you get past 0 or once you get past 1, whatever, instead of things jumping immediately, it scales its way up. And so you get a continuous output. And so it would be exactly the same kind of situation, but the output in this case, rather than being 0 or 1, would be a number between 0 or 1. And it would correspond to the probability of belonging to a certain whichever data class that we were talking about. So if we were using a logistic function with a neural network, or again with a whether it's a single perceptron or a collection, a chain of these perceptrons, the output would be a probability, and the probability would be, here's the probability that the room was occupied. Rather than saying the room is occupied, we say we're 87% certain that the room is occupied, but there's a 13% chance that it's not occupied. And so we would get outputs that would correspond to the different categories. And so what happens in this case, again, is we set like a threshold, and we say if a threshold's above this, then something happens, and if it's below this, then the other thing. We fire this neuron if the output is big enough, but rather than saying just 0 or 1, we can put numbers in between. So if a neuron gets enough input, then it can send its value on, but it would send maybe a weakened value instead of sending on the whole value. Or in other situations, whatever input it got, it goes ahead and sends it on. And so what happens, or excuse me, whatever output it creates, it sends it on. And so what can happen in this case is you can get this neuron and this neuron and this fire all very weak, but together, as they feed into the next one, all of that input together is enough to cause the next one to fire. Or they Whereas before, if it was all or none, now it can be a bunch of like weak signals, and the weak signals can build up enough to cause something else to happen further on. Okay, so when we talk about a perceptron, perceptron uses the Heaviside function, and the term that gets used in the other case is a sigmoid perceptron. Let's see, Liam, going back, I'm sorry. This is just the input. So in our case, what are we inputting? We would be inputting a dot product. So that's just whatever the it's the H. Well, like the H, right? The H, you inputted the weights were part of the process. So it's the logistic function itself is like the H from before. The H from before took in an input, but the weights were built into that. So you would do the dot product of the weights with the input, and then you looked at that to see whether you were going to output a 0 or a 1. What happens now is you take that dot product with the input and the weights, and then you put that into this function to see what goes on. So rather than just seeing if the dot product was positive or negative, now we take that dot product and put that in. So like that. Okay. So we end up with this idea of being able to update a perceptron. We update a perceptron by seeing how close it came to the real answer and going back and making updates. But we need a sigmoid perceptron update rule. And the sigmoid perceptron update rule has to use calculus because it's based on that function. But the nice thing is we don't have to go through all of that. If you want to go through that and understand where it comes from, it is worked out in section 18.7, I think, in the text. But we can talk about it individually if you want to know where it comes from. The formula is based on how close were you to the answer, and seeing, okay, I'm a little bit off from the answer, so that means I have to look at the difference between where I am and where I want to be, see how much it's changed. So how much of a change to the input do you have to make to create this change in the output. So it's based on derivatives. But the nice thing about functions like the logistic function, the derivatives involve e to a power, and so the derivatives are pretty nice. And so what happens is we still end up with our alpha involved. I'm going to call the logistic function, I will do, I'll use like, I don't know, capital L or something. Okay. So looks a little messy. But turns out that part of this comes from the derivative. This part comes from the derivative. This part is the right answer. So again, we're saying how far away from the right answer are we? Multiplying it by our alpha, which is how much of a change we want to make. This is coming back to what was the actual input, and then seeing how much of a change you're making to the existing weight. And so you go through again and work your way back, uh, making up a value for the weight and seeing how close you came to the real answer, and updating accordingly. Okay, so L, this is the logistic value. This is involving the dot product of the existing weights with the vector x, and then the individual input has an effect as well. All right, so what is this? This formula comes from using calculus. We ended up being a little wrong at the end. If we're wrong at the end, how do we adjust that? So it's what kind of change do you have to make on the input in order to get the necessary change on the output? And that's what calculus does, right? It's looking at changing something on input side to see what happens on the output side, except in this case, we're looking at it in a backwards order, saying, oh, it has this answer at the end. How do I change it at the beginning to get the answer that I really, really wanted? Okay. So at least roughly conceptually, does that make sense? Okay, so and then there's that difference, right? When you start to implement something, that's where the making sure that we understand what exactly all the pieces are. So main thing for now is that rough idea, at least, of what's going on. All right, so let's take a look at a couple of examples, not specific, not working through them, but talking again some more conceptual examples. There's a problem that came up before when we were looking in lab 7, I guess, when we were doing a calculation. We needed a majority function, right? We needed to see, were the majority of the votes for occupied, or were the majority of the votes for unoccupied? So this problem, this function, or this question is given n inputs, again, just thinking of binary inputs, if we think of n binary inputs, the question here is, are more than half of them equal to 1? Turns out that this kind of situation can be easily described by a perceptron. Um, of knowing from the inputs whether more than half of these binary inputs are equal to 1, uh, that is a linearly separable situation. We can do this. However, another approach that we've had for making decisions in the past, this would be very difficult for a decision tree to be able to make the choice um, of or being able to reach that conclusion. Are more than half of them equal to 1? On the other hand, if we had some kind of maybe we were going to try to decide, as an example in the text, there's a restaurant example that says, let's decide what we're going to have to eat. A whole bunch of different conditions, what day of the week it is, what time of day it is. I can't remember, a whole bunch of different attributes that are considered there. That is something that's fairly easy for a decision tree to do. Would be very difficult or actually probably impossible for a perceptron, because it wouldn't be linearly separable. So a single perceptron wouldn't be able to decide what to order, whereas a decision tree, you would be able to decide. It might be a big tree, but you'd be able to decide what you wanted to order. So and just emphasizing if they're not linearly separable, cannot be solved by a perceptron, but in some cases they might be quite easy for a decision tree, or in other cases the decision tree might still be really, really big as well. Okay, so the last thing I just want to tie this into neural networks in general, and we can, well, then we'll stop for today. All right, so already said this actually, but how do we create a neural network from perceptrons? Create a neural network from perceptrons. We can just just put them together. How do we put them together? Well, that's where the art part of neural networks comes from, right? So what kind of questions do we have? We might have a question of how many inputs do we need? How many layers do we need? How many nodes in each layer? How many outputs? These are all the kinds of questions we have to ask in trying to decide how to construct a neural network. Of course, before you ever get to this point, we have to determine whether or not neural networks are even the method that makes sense. But when we get to a point where that does make sense, then we have to start thinking about, okay, how many inputs are we going to have? How many layers do we want to use? How many nodes in each layer? How many outputs? So if we were looking at our Lab 7 data, the room data, how many inputs do we need? Yeah, so one input for each attribute that we have, right? We don't need more inputs than we have data to put in. So we'd have 5 or 6, depending on what we were, how we were going to use that data. So that's how many inputs. Well, how many layers or nodes in each layer? That's a little, well, again, that's something that we'll talk about in just a second. How many outputs do we need? Well, the idea was that we're going to say occupied or not occupied. So we could have two. Um, so ultimately we want two, but we might be able to do something where you just have one that gives you an answer, and if it's not that answer, then it's the other answer. But if we're doing this with a sigmoid perceptron, we're going to get percentages or probabilities. And so you might do have the two outputs. So usually, if you have two answers that are possible, you would have two outputs in this situation. What if we were going to? What if we wanted to do written analysis of handwritten digits? Let's say handwritten digits. How many inputs would we need for a neural network analysis of handwritten digits? How many outputs would we need? How many let's go to outputs first. That'd be, yeah, one output per digit, right? So 10 outputs, something for 0 through 9, and we would have a probability of being in each one of those categories. How many inputs? Well, inputs, that's going to depend on how we try to set things up, right? So one way I've seen is we say, okay, all of our digits have to fit inside this box. So we're going to have the handwritten digits, but they've been scaled so that they fit inside inside this box. And then one approach, this isn't even a straight line, using the straight line. One approach will break that into a grid and then feed each one of these rectangles or each one of these squares on the inside. Feed it's a black and white character that's been drawn, and just feeds what's in that box as a separate input. And there's been some interesting results in terms of being able to recognize something by looking at just a tiny little piece of what's happening. So how many inputs? It's going to really depend, right? If you were solving that problem, the number of inputs really depend on how you're trying to tackle the problem. So what happens in all of this? We have some approach of creating a network. This network has nodes that correspond to inputs. There's arrows going to things in different layers. How many nodes are in each layer? How many layers are there? Arrows going to the output. So one approach we can have is to have a fully connected network. A fully connected neural network is what we've been looking at so far. A fully connected neural network has all these inputs, how many ever inputs there are, whatever's happening in the next layer. Everything in each layer connects to everything in the next layer. If you had 50 nodes in some layer, then you would have every single possible connection being there. On the other hand, you can have some that are not fully connected, so you don't every possible edge. And so if not fully connected, we would need some kind of effective search procedure. Again, we're back to searching. Everything's about searching. There'd be lots of possible connection topologies, and we would need an effective search procedure that would go through those to find a possible right answer. Okay, so I'm just going to mention two of these, and then we'll stop for today. So one of these approaches is called tiling. In tiling, you begin with a single unit, like a single perceptron or a single piece. That predicts as well as possible for what you have. And then you slowly add to it. You add new units to take care of the training data that the first single unit got wrong. And you add just enough to take care of all the training, data, right? So begin with something easy and just keep adding to it until you get to the best thing that you can get for covering all of the training data. So this is one method. There's another method that might be appropriately named given today's date. Called optimal brain damage. It's actually what it's called. Optimal brain damage. You start with a fully connected network. Then you drop some of the connections and retrain. If the performance is not decreased, what happens? If the performance does not decrease, that means that those connections weren't necessary anyway, so you repeat it. If the performance does decrease, then you put those connections back in, right? But if the performance does not decrease, then you can drop some more connections, retrain, and see what happens. Same performance. So what's going to happen? We get a simpler network. There's fewer calculations, less work that has to be done. And so so the optimal brain damage starts with a really complicated network and then throws away pieces that turn out to not be that important. And actually, not just the edges can be thrown away. Sometimes it turns out that some of the units themselves, some of the attribute pieces, or some of the nodes aren't necessary. If they're no longer connected to things going forward, then you can throw those away as well. So if there's nothing coming out of the right-hand side of one of the nodes, you can say, hey, it's not useful anymore. Drop that one, and then that gets rid of all the connections leading into it, and again, saves a lot of work. So, but what do you have? You have more training time up front, right? You have to train a fully connected network. Drop some of the connections. How do you go about dropping those connections? Sometimes it's random. Sometimes there's other reasons, some other input on which connections to drop. Drop some connections, retrain, see what happens. If you get the same performance, drop some more connections. Keep going until you can't drop connections, and then you have a better trained situation, maybe. Okay, so excuse me. So going from a perceptron to a neural network is basically just gluing pieces together and finding the right the right mix of all of the pieces. Okay, so what do we have? We have labs 9 and 10, which involve neural networks. Lab 10 actually involves implementing the neural network on that same lab 7 data sets. Um, given the situations, if you can, for lab 9, even if you don't get the full version implemented that's in the lab, if you can implement the perceptrons and actually have it calculate correct weights for and or, then that will be that's a big part of the task anyway, right? So that would be a passable point. You don't get the full extent of lab 10 of applying it to that data. That's not going to hurt you too much. You also notice on Blackboard that you have quiz 4. Quiz 4 would have been in class on Wednesday, but I don't want to make you do that during that time slot. So you have it, and it's due May 8th. So the end of our final week, right? So, any questions? You don't want to put it off until May 8th to start, though, right? It's due at 1 o'clock. I need to have time to get it graded and be able to get grades in. And you definitely don't want to put it off that long.